So the first problem say like this is the number 53. It say a closed surface. So I will picture a closed surface. It doesn't say if it's a sphere, it's not. It has a net charge of 2.5 inside. Inside there is a 2.5 microcoulomb by 10 a la minus 9 coulombs. It say if you find the electrical flux, what is the electrical flux? The electrical flux is the sum of E sub I, A sub I, cosine of alpha sub I. This is the electrical flux. You know where is the charge. You don't know where is the charge. You know that it's inside, but you don't know where exactly is the charge. But you know that inside the surface, inside the volume, there is a charge, and the magnitude of the charge is Q sub I. What is the flux? Well, Gauss' law says that the flux is Q inside divided by epsilon 0. Okay, so what is the flux? Very easy. The flux is Q inside 2.5 by 10 a la minus 9 divided by epsilon 0. 8.85 by 10 a la minus whatever. So this is the flux. The answer is done. The part, yes?
What? It's 2.5 times 10 to the negative 6, not 9.
6. Oh, sorry, 6. Yes, it's microcoulomb. What is the net electrical flux of the surface? We found. Let's go to the part B. The part B say, if the electrical flux through the closed surface is determined to be 1.4 newtons meter square divided by coulomb. This is the flux. If the flux is this, if the electrical flux is this, how much charge is enclosed in the surface? Oh, it's something incredible, but I have the flux that I have, that is E by area, that is Newton divided by Coulomb by the area. In this case, the flux that I have, they say, if you have a total flux, if you have the sum of E sub I by A sub I by cosine of alpha I, and you measure, you make the stupid thing to take your time to measure, and you measure that is 1.4 plus 1.4. So the flux go out because it's positive. Because if it's negative, the flux will go in. So if you measure, what is the charge inside? Well, Gauss' law will tell you the charge inside is epsilon 0 by 1.4. What is epsilon 0? You look for epsilon 0, you multiply by 1.4, and you get the charge inside. This problem say a point charge of 8 nanocoulomb is at the center of a cube. So I will draw a cube. A cube have a length A by A by A, have the length A, this is A, this is A, and the volume is A cube, of course. This is the volume of a cube. So you start at the center of the cube, at the center, just of the center. You store a charge Q. So the charge Q will produce an electrical field in all directions. Wow! It will be very difficult. I have to go to the surface here, and I have to calculate the electrical field by the area. Almost impossible task, because when I go at these regions, the electrical field will go like this, and the area will go up. When I go at this region, the area will go like this, but the electrical field from the charge will go like this. It will be something very complicated. But Gauss' law have a solution. It says, what is the electrical flux? The surface of the cube. It means the whole surface. How many surfaces have the cube? How many surfaces have a cube?
6 surfaces?
6
Six,
surfaces.
Professor.
6 surfaces. Okay. What Gauss' law say? If you have 6 surfaces and they made a closed surface, the flux about the closed surface, about the 6 surfaces that are closed, the flux is the charge inside divided by epsilon 0. So, again, it's the same thing, the same trick. What is the electrical flux? Well, the charge inside divided by epsilon 0. They give me the charge. 8 by 10 a la minus 9 coulomb divided by epsilon 0. So I know what is the flux. I don't have to calculate. I don't have to calculate the sum of E sub I, A sub I, cosine of alpha sub I. It will be a mess of calculation. But now it comes the question V. The question V is very interesting. What is the flux for one of the side, S, for this, for example? If you place the charge in the center, what is the flux through one of the surface? So you will think like this with a symmetry, with an argument of symmetry. If the charge is inside, and exactly I put it on the center of the cube, any of the surface of the cube, they have the same priority for the flux. They will be the flux that I will calculate E by the area, by the cosine of the angle, of course, E by the area. The sum for every surface will be the same. So if I want the flux for one of the surface, any of the 6, will be the same total flux divided by 6. So it will be 8 by 10 a la 9 divided by the value of epsilon 0 divided by 6. And this will be the flux through any of the side of the cube. But if I move the charge from the center and I put it in one side, let's say that I put the charge not in the center, and I put it, instead of putting here at the center, I put the charge here, this not will be the result. There will be another different flux from here. This side will not have the same flux than this side. I need to put the charge just in the center. If I have the charge in the center, I can think of an argument of symmetry. Okay? So let's go to do another problem. Oh. On here, what I have explained is how to calculate the electrical field using Gauss' law for this example, a very long line of charge. You have a very long line of charge like this one, so the very long line of charge, it will produce an electrical field at any point P. So at this point P, for example, at this point P, it will produce an electrical field. What is the sensible thing to think about the direction of the electrical field? Well, if I go further, the magnitude of the electrical field, I can suppose that will be weaker. But the direction will be always in this direction. I cannot think that the direction is like this, or I cannot think that the direction of the electrical field can be like this. The symmetry of the problem, the fact that there are so many charges up to this line, to this yellow line, that down to this yellow line, it makes me to think that there are so many contributions in this direction that in this direction. So the sum will be in this direction. So I can think that the electrical field is always like this. So using the facts that the electrical field is like this, imagine that you are going to apply now Gauss' law. So see this picture and you will see that you can construct a cylinder around the cable, where the cable is charged with positive charge, And you can imagine that at any surface, the electrical field will go radially out at any point of the surface, radially out. So you can say that through the surface, the magnitude of the electrical field will be the same because they are far from at the same distance from the axis, for the line of charge. So if you want to see a picture from this point of view, you will see the cable going at any point. The electrical field will go in this direction, always radially. There is no other way to think due to the symmetry. At the distance r, the symmetry will say that all the magnitude of the electrical field will be the same. So this will be the electrical field. So knowing that, we'll construct the Gaussian surface. What Gaussian surface? We construct a cylinder, a big cylinder that surround the charge, surround the cable. And inside this is a closed surface, this is closed, this is closed. Inside this, there is an electrical field going out. Going out, this is a flux because the charge is positive. So I will find the flux, the electrical field by the area. And once that I found the flux, I will say the flux equal to the charge inside divided by epsilon 0. Doing that, I will find the flux, and the flux will be the electrical field E by the area, but the area of the surface, because it's the area of the surface of the cylinder, you cut it here, the cylinder, you take the cylinder, you cut it, you open, and this will be L, and this will be 2 pi r. So the area will be 2 pi r by L. So the flux will be E by the area, E by 2 pi r by L. But Q inside is the charge inside. So through the cable, it will exist a charge per unit of length. This is what we call lambda, the density of charge. So the density of charge is the charge per unit of length. So the charge is the density of charge by the length. So I will put it here in this the charge inside. The charge inside is here. The charge inside is just here. It's just inside this, only this piece. It's lambda by L is the charge inside. So I will put the charge, the value of the charge inside, that will be the density of charge, let's say 3 coulombs per meter by the height of the cylinder, let's say 3 meters. So 3 coulombs per meter by 3 meters will be a charge of 9 coulombs. Okay, so the electrical field, the L will go, and this is the electrical field. This is the electrical field produced by a line, very low line, that is charged with positive charge, everything distributed uniformly, very, very, very low, and the charge at any point P will point in this direction and will have, at the distance r, will have these magnitude, the magnitude. So the other thing that I did here, it was Gauss law for a ping pong ball. A ping pong ball that is full of charge. Let's go to calculate the Gauss law for a ping pong ball. Gauss law to a ping pong sphere. So the sphere is empty, it's a hollow inside. There is nothing inside. The charge is on the surface. I'm going to apply Gauss law to this problem. The problem of a sphere that is empty, and in the surface of the sphere there is a charge, and the density of the sphere, or the density of charge, is constant. The density per unit, the charge per unit of area, is constant. So I want to find the electrical field here at the point out of the center. I might have to find an electrical field inside. So using the argument of Gauss' law, it allowed me to find the electrical field at any point outside and inside. So if it exists an electrical field outside, I will think that the electrical field will go like this. So it will be E by the area, E by the area, E by the area. If I walk around the whole surface of this imaginary surface, it will be E by the area. This is the flux. And E by the area will be the magnitude of E by 4 pi r squared, the radius of the imaginary Gaussian surface. And this will be Q inside divided by epsilon 0. So the electrical field outside, the magnitude of the electrical field outside, will be the charge inside the volume, inside the Gaussian surface, divide. So it looks like the charge, instead of being here, distributed here, it will appear like the charge is on the center. And the electrical field produced by this pinball distribution of charge will be equivalent at the electrical field produced by a charge that is all the charge concentrated, like I pick up all the charge in the surface and I put it on the center. It will be the same electrical field like a point charge in the center. So this is the magnitude of the electrical field. Now, let's say that I want to find the electrical field in the center of the ping pong ball. This is the ping pong ball, this is the ping pong ball. In the center of the ping pong ball, I don't need to use Gauss' law. I can imagine that this small charge, positive, will produce an electrical field in this direction. I can imagine that this positive charge will produce an electrical field in this direction. If I imagine for every pair of charges, I can imagine that the electrical field at the center of the sphere is 0. So I don't need Gauss' law. But what if I move this point and I put this point P here? The calculation will be very difficult because it will be due to this charge will be an electrical field like this. Due to this charge will be an electrical field like this. Due to this charge, it will be an electrical field like this. Oh, and how I will sum it will be really difficult. But Gauss' law have the answer using symmetry arguments. And the symmetry argument is like this. If it exists any electrical field, it will go maybe like this or maybe going in. I will tend to think that if it exists an electrical field, because this is positive charge, I will tend to think that it will go like this, going in, not going out. But it doesn't matter. So Gauss' law says, calculate the flux. I already calculated the E by the area because the electrical field and the area are both. The cosine of the angle is 0. It will be E by the area. So E by 4 pi r squared will be Q inside divided by epsilon 0. So what is the Q that is inside this radius r inside the ping pong shell? Well, the charge is here outside, so there is no charge inside. So the charge inside is 0, so I can conclude that the electrical field is 0. This argument is quite difficult to make the calculation. So to make the calculation using Coulomb's law. So the calculation will say that the electrical field inside of a sphere of charge, a ping pong charge that is empty inside, the electrical field is 0. At any point, not in the center only, at any point. This is what Gauss' law it will say. So we'll go to the next problem. So this problem is say like this. It says you have a spread, something that the spread paint, and the paint have some kind of charge that is produced by the friction with the air, and it produces some electrons are transferred to the paints, and this made the paints to work in a better way. All the painting they produce this kind of effect that they charge. They make a small charge on the surface, so they attract particles, so the painting will look much more better. So let's say that you have a surface plastic, a sphere. This is the sphere, the green one. And in the green one there are a positive charge, and the diameter is 19 centimeters, giving a charge of minus 9 coulombs. Sorry that I draw positive charge, it's minus 9 coulombs. So correct, this is minus 14 coulombs, 14 by 10 a la minus 6 coulomb. Find the electrical field just inside the plane layer. Well, I did it. I did it before. Just inside the plane layer, the electrical field is 0. B, just outside the plane layer. Outside the plane layer, I already did it. The electrical field will be, I construct outside the plane layer, I will construct a Gaussian surface. This Gaussian surface, the yellow one, this Gaussian surface, outside the plane, and I will say E by the area, the flux, E by the area. In this case, the cosine is cosine of 0, because I imagine it will be cosine because the electrical field is going in this direction and the area is going in this direction. It will be a cosine of 180, that it will be minus 1. So this flux for this case is negative because the charge is negative. Sorry that I did it with a positive charge. I didn't realize. So the electrical field, the magnitude of the electrical field by the area will be E by 4 pi r squared, and this quantity will be negative because the flux will go inside because the charge inside is negative. So this is the flux. So what will be the electrical field will be Q inside divided by 4 pi r squared. So the magnitude of the electrical field outside will be 4 pi x 0 r squared. But if I'm going very, very near the layer of the painting, the layer of the surface, but from outside, this radius r will be equivalent to the radius r, so I can find the electrical field very, very, very near. Maybe you can make this calculation sigma divided by x 0, or maybe you can see this calculation will be correct. Sigma is the total charge, the minus, I don't remember, microcoulomb, divided by the total area, 4 pi divided by r squared, the radius. This is the density of charge divided by x 0. If you make this calculation, you will find that this should be equal to this, because this is the electrical field produced by infinite plates. So if you are going very, very near the point, very, very near the surface, here, very, very near the surface, it will look like a plane. So the electrical field, I have proved you that, it's a 2, it's a 2, sorry, it's a 2. I have proved you that the electrical field is sigma divided by 2x 0. So doing this calculation should be equal to doing this calculation. Oh, yeah, and I see it. I see it, that is the same calculation. You can see it's the same calculation. So let me put, instead of capital Q, Q inside. And it's the same calculation for sure. So this problem is done. And let's go to the next problem. Oh, no more problem. Okay, good luck.